Good morning. So we are going to start this lecture on control design using polynomial methods. So in the previous lectures, we considered how to make a feedback of the state, and the specifications were made in the form of specifying the closed loop poles. So you do what we usually call pole placement. That is to say, we specify the desired positions for the poles of the closed loop system, of the control system, the plant that we want to control together with interconnected with the controller. And then we design the controller based on this specification. But the zeros depend on the type of options that we consider. I mentioned to you that there are several possibilities for including the reference, and this corresponds to different zeros. Now, in this design, we are going to be able to impose the zeros as well as the poles. So our specification will be made in the desired or reference transfer function. Furthermore, before we were considering the feedback of the state. Actually, when you don't have access to the state, use an observer. And the observer reconstructs the state or builds a state estimate based on output observations as well as input observations. So actually, you are relying on a feedback of the output even when you do state feedback, because you have the observer that reconstructs the state from the output, and then you feedback the state estimate. Now, in this chapter, instead of using this association of state feedback and state observation, we are going to work directly with transfer function models. So that's why we call it controller design using polynomial methods, because we are going to use the polynomials, the numerator and the denominator, the polynomials that define the transfer function. So what are our admissible control laws? They are written in this form. So you have a polynomial in the forward shift operator. I call it R of Q. Q is the forward shift operator. Remember that if you apply Q to a sequence X of K, you get the advanced sequence X of K plus 1. And R of Q is a polynomial in this forward shift operator. So is Q up to some degree. I denote by this partial differential symbol to del R is, you should read the degree of polynomial R. So Q up to some number plus a coefficient R1 times Q up to some number minus 1 and so on up to a constant. Okay? So don't get confused with the reference, because this is just a polynomial. And so on the left, we have only a linear combination of U and its shifted values, U of K and these shifted values. Then this must be equal to some polynomial T of Q, filtering the reference. Now this is the reference, okay? Don't get confused with this reference signal and the coefficients of R. Again, I think it will be clear from the context from now on. Minus, and this minus is just a matter of convenience because it implies on the signal of S, minus S of Q, another polynomial filtering the output. Okay, so let's see an example. Let's see an example. And suppose that Q is a first order polynomial. T is a first order polynomial, but with no independent term, and S is also first order polynomial. So you write your control law in this form. And since Q is the forward shift operator, so Q UK is U of K plus 1. And R1 of UK is just R1 times UK. And T0 QRQ is T0 R of Q plus 1, and the same thing for Y. Okay. Now, if you delay everything by a unit time, you get UK plus R1 U of K minus 1, etc. So this is just the expression above delayed by 1. Now, you solve it with respect to UK. What does this mean? It means that your UK is a linear combination of what? The control in the previous sample, the reference at the same sample that you know, the output at the same sample that you also know because you have read the signal from the AD converter, and the output at the previous sample that you have in memory. Okay? So if you want to implement this control law in a digital computer, it's very simple. It's just what you need. You need some memory to know past samples. And you, of course, you must know these coefficients R1, T0, S0, and S1. Okay, so this is not arbitrary, it's your controller. And you do a linear combination of these signals. So you only have to, the only operations that you have to do is to recall signals from the memory, read signals from AD, and then multiply signals by constants that you have previously computed. Now, of course, you must know what is the order of these polynomials and what are these coefficients, okay? So that is what we are going to learn. For the moment, I would like you to just understand that when you write, let's see again the previous slide, when you write your controller in this form, you can translate it in a very clear way to something that you can implement in a computer. Okay, so this is a compact form of writing this controller that you can easily program. Okay, so this is what I have just said. When you study the slides, you can read it. Okay, so what is the structure that we have? Well, you have your plant, and I assume that your plant is described by a transfer function. So a polynomial b divided by a polynomial a. Okay, and we know that we can think of the transfer function in z variables. And if you replace z by the forward shift operator, you have your so-called impulse operator of the plant. So what is really important is that you have a polynomial divided by a polynomial b that gives you the zeros, divided by a polynomial a that gives you the pulse of the plant. Okay, and then you feed back. D is probably some disturbance that affects the output, and you feed back the output, and then this block as well as this block, they are your controller. So you have a feedback controller, which is described by S divided by R, and a feed-forward controller. So it's T divided by R that filters the reference R. Okay, so remember that if you look here, and if you divide everything by R, what you get U of K is T divided by R filtering the reference, minus S divided by R filtering the output, which is what you can see here. What is the role of these blocks? Well, this is a feedback block. Okay, S divided by R is a feedback block. So what is the role of feedback? To reject disturbances, to reduce the sensitivity to modeling errors, and to stabilize the system. Okay, this is the function of this S divided by R. It's the classical function of a feedback controller. Now you have this, which is a kind of anticipation of our feedback block that filters the reference so that you apply not the true reference, but a filtered reference to the system. Imagine that your system was highly oscillatory. Now, you know that at some frequencies, if you excite these frequencies, the system will oscillate a lot. Of course, you can do pole placement by designing S and R. But you can also play with this polynomial T to avoid that the components of the reference in the frequency range in which the system oscillates are present. For instance, in your laboratory, you can think in intuitive terms in this way. So the bar is a flexible bar, it oscillates a lot. So you can put here a low pass filter to avoid the first peak of oscillation, the first mode of oscillation. Okay. If you like to use, if you are a soccer fan, you can think of this. So you have a line of defenders. Okay, when you are defending, you have a line of defenders, and then in front of the line of defenders, you have the so-called player number 6, who is a guy that is disturbing the strikers, the opposite strikers, so that they disturb their activity and render easy the activity of the line of defenders. Okay, so the line of defenders is S divided by R, and this number 6 player is T divided by R, is in front, okay, making the first line of defense. And the idea is that by including this term, you can improve your performance. Okay, so but before we move on, let me make you a comment. Later, we are going to see that R will may incorporate an integrator. And in this way, you are using integral control. You are forcing an integral action, which is necessary when you have to track Y with precision. When the reference R is constant, you want Y to track it with zero steady state error. Then you force an integral in your controller. And this is made by forcing R to have an integral action. Later, we are going to see how. Now, if you are integrating something here in this block, and you are also integrating something here in this block, you will be finite and will tend to a value which is constant, that keeps Y close to R, only if there is a balance between this signal, which is growing because you have an integrator here, and this signal here, which is also growing because you have an integrator here. Okay? So this is clearly not practical, because after a while, this signal will saturate. Imagine that R is a constant. If R is a constant, this signal here will grow if you have an integrator. So although this block diagram is something that appears in all the books that are related to polynomial design of controllers, what you do in practice is to move this factor 1 divided by R here and here to this point. And you have an equivalent block, which is in which your integrator is inside the loop, and you don't have these saturation problems, because now you don't have signals that go to infinity, because the input of the integrator will go to 0. Of course, there are some problems related to causality. Later we are going to see. So to do that, you have to put here a polynomial, which is just a forward shift polynomial up to the greatest power of t and s. Okay, but that is something that we are going to clarify later. So bear in mind that if R has an integral action, then you cannot program in Simulink your blocks like this, but you have to move this R to here. Okay. Now, one thing that you want is that your controller is causal. So causality means that the manipulated variable u at time k does not depend on future samples of the variables from which it is computed. So the output, possibly accessible disturbances that you can use to improve your controller. And you know that for this to happen, let's see again the block diagram. Both these transfer functions, S divided by R and T divided by R, must be causal. That is to say, the number of poles, that is to say, the degree of R, must be bigger than the number of zeros. That is to say, the degree of R must be bigger than the degree of S, and here the degree of R must be bigger or equal to the degree of T. Okay, so degree of R bigger or equal to the degree of S, degree of R bigger or equal to the degree of T. These are the causality conditions, okay, that I wrote here. Let me give you an example. Suppose that we have our first order controller, okay, and you repeat what we have just seen. So u of k plus 1 will depend on what? R of k plus 1, y of k plus 1, and its past. So, okay, if you delay everything to have UK will depend on R of k, the reference. Sorry, this you see is the same as R. U of k and y of k minus 1. Now, suppose that S is a second order polynomial. So R is first order, but S is second order. So you are violating this condition because S is bigger, is degree 2, than R, which is of degree 1. What happens? If you write down the equations and you expand this, what you get y of k depending now on u of k depending now on y of k plus 1. That is to say, you are at time k, you want to compute the manipulated variable u at time k, and it will depend on a future reading of the output. And this is non-causality, okay? And this happened because in this case, S is as a degree bigger than R. So for causal controllers, we must comply with these two conditions. Would you like to make some question at this point? Is everything clear? Okay. Now, look again at the diagram. So one important thing is the loop gain. The loop gain is you interrupt the gain at some point, for instance here, and you multiply all the transfer functions. So B divided by A times S divided by R. And this loop gain, you know, must be big when you want to track a reference or disturb or reject a disturbance. Must be small when you have noise, so typically in the high frequency. So the loop gain is an important thing. And one thing that we can do is to force the loop gain to have integral action. Okay, so one thing that we want is to force this R polynomial to have a pole at 1. Remember that a pole at 1 is integral action, means integral action, because it corresponds to add something. Okay, so your R of Z polynomial, or R of Q if you want, is Z minus 1 up to the number of integrators. Lambda is the number of integrators, usually lambda equal to 1 or 0 if you don't need an integrator in your controller, because, for instance, the process has already an integrator. And then you still have some polynomial that I call R1 prime. Okay, so this prime is nothing more than part of the notation, meaning that this is a different polynomial from R. R is made of the product of Z minus 1 up to lambda. We have to decide how many integrators we have, usually something that you decide, multiplying this R1 prime. So just a moment. Let's go back to this slide. Okay. Let's go back to this slide. You have your plant, you have your controller. Okay. The plant is described by B divided by A. And you want the transfer function between the reference and the output to be some HM. So this is not H, it's HM. There is M missing here, which is some BM divided by AM. Okay. Now, I'm imposing something. And one of the things that I'm imposing is that both B and A, okay, this system is causal, so the degree of A is bigger or equal than the degree of B, and there are no common roots. We say that the polynomials B and A are co-prime. Co-prime means that B and A have no common roots. And the same for AM and BM. Okay? Now, this looks a little bit mysterious, but well, it looks natural that we work with the simplest possible models. Okay, if we have common roots, we can cancel them. If you don't cancel them, then you get into trouble. From the mathematical point of view, you will get into numerical problems. Okay, so the equations won't have a solution. The equations that we are going to establish don't have a solution. And but what can be seen from a deeper point of view, which is, I'm not going to show it to you, but that's the situation, is that this imposition that B and A have no common roots corresponds to the controllability condition. Okay? Both controllability and observability conditions. Remember, we mentioned the controllability condition as some matrix having a rank equal to the order of the system, and it was an initial essential condition for the pole placement solution to have a solution, for the pole placement problem to have a solution. Okay? Also, the observability condition is again another condition that forces or that allows the design of the observer to have, the observer gains to have a unique solution or to have a solution at all. Okay? And actually, you can show that if the system is both controllable and observable, those matrices have rank n. This corresponds in terms of transfer functions not to have common roots. Okay? So this means controllability, that the system is controllable and observable. Okay? But if this is very complicated to you, just think that we do not allow common factors both in the plant model and in the desired plant model. Okay, I call this sometimes the reference model. So you want the system together, or the system together with the controller, to behave as a BM divided by AM. Okay, remember that there is an M missing here, so this is not that H. Okay. Now, so this is the problem. What is the strategy to solve this problem? What would you do to solve this problem? So the problem is find polynomials R, S, and T such that this closed loop system has transfer function BM divided by AM. So where can we get equations satisfied? Where from can we get equations satisfied by R, S, and T? Can you give me one idea of how to proceed? I repeat this in Portuguese. O nosso problema é descobrir ou calcular os polinómios R, S e T de tal maneira que o sistema controlado, dado B e A, se comporte como um BM sobre AM. Então, qual é a estratégia que eu posso seguir para obter equações satisfeitas pelo R, pelo S e pelo T? Depois resolvo essas equações e tenho o R, o S e o T. Então, onde é que eu posso ir buscar essas equações? No ideas? No brave men or women? Não há nenhuma padeira de algebarrota do controle capaz de... Não? Ninguém tem ideias? Como é que eu posso atacar este problema?
Se calhar podíamos dividir o bloco do controlador em um bloco para que atuava primeiro no... Transformar este diagrama de blocos num diagrama de blocos que fosse mais fácil para nós escrever.
E qual era o mais fácil de todos? Repara uma coisa, José, não é? Estou a falar com o José Neves, não é?
Sim.
What is the you want the transfer function between R and Y to be BM divided by AM. So this is something that comes from your specifications. So somehow you decide what is BM and AM. Okay, so you impose the poles and you impose the zeros. Now, what would you like? This is a transfer function. This is a feedback transfer function. Okay. So if you think of having an equivalent transfer function, which transfer function would you obtain? Let's forget about D. Okay. Suppose that D is not present. Qual era a função de transferência mais natural para pensar?
Estou a perceber a pergunta, professor. Desculpa.
Não percebeste a pergunta? Tu disseste assim, vamos tentar obter uma função de transferência mais simples. Não é? Eu não sei se ela é mais simples, mas se calhar há uma função de transferência natural para este problema. Porque tu queres... Diz?
Seria entre a referência e a saída.
Portanto, se eu obtivesse a função de transferência entre a referência e a saída, I will say this in English in a moment. Se eu obtiver a função de transferência entre a referência e a saída, não é? Ficava como uma função de transferência parametrizada pelo R, pelo S e pelo T. Depois a seguir o que é que eu vou fazer? Há um passinho mais. Tenho essa função de transferência e agora o que é que eu posso fazer com ela? Qual é o teu objetivo?
Vou descobrir onde é que estão os polos agora e depois vou dimensionar R, T e S de forma a que esses polos fiquem onde eu queria.
Sim, mas como é que fazes isso? Tu sabes, podes obter a função de transferência parametrizada pelo R, pelo S e pelo T. Ficam lá umas letras, não é? E tens a função de transferência. E agora queres obter uma equação. Sabes que isso tem que ser o quê? Qual é o teu objetivo? Está aqui embaixo.
Sim. Pôr a função de transferência nessa forma.
Que ela seja isto. não é? Eu queres que ela seja isto. Portanto, calculas a função de transferência e agora igualas a esta que tu queres. Uma coisa é a função de transferência em função do R, do S e do T. A outra é aquela que tu especificaste. Agora tu queres que elas sejam iguais. Ok? Está claro?
Obrigado.
Okay, so the strategy is compute the closed loop transfer function. This is parameterized by R, S, and T. And now you know what is your objective. Your objective is written here. You want your closed loop transfer function to be BM divided by AM. Remember, BM and AM are given. Okay? So if you equate both transfer functions, you have an equation that you must solve in order to R, S, and T. So let's proceed a little bit. Maybe things become a little bit more clear. So let's start by computing closed loop transfer function. You have your system, which is y equal to b divided by a u, or a y equals to b u. And you have your controller. Okay? Now, you want to get rid of this common term u. So multiply everything by r here. So you get ar y equals to bru. And multiply everything by b here. So you have bru equals to btr minus bsy. Okay? Now you have bru and rbu. So ray is equal to bt blah, 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 blah. Okay? So you can equate this term to this term. This term multiplied by r is this term multiplied by b. Okay? Just algebra. Clear? You understand the algebra? Now you can rearrange things because you have here terms in yk and in yk, so you make it go to the other side. This is a big kick in mathematics when we say that one term jumps to the other side, but okay. And so we have this, we have a polynomial filtering yk equals to a polynomial filtering rk. So the transfer function between the reference and y is nothing more than bt divided by ar plus bs. Is it clear that this is a transfer function? And now you want to impose that this closed loop transfer function is bm divided by am. So you get, this is an equation, and you are looking for values for r, s, and t that satisfy this equation. Could you understand this? If you don't understand, just tell me. So I did two things. One thing is to compute the closed loop transfer function. And this is just algebra. So I pick up the process model, I pick up the controller model, and I eliminate u among both of them. Okay? So I do a trick of multiplying and equating and so on. So I get this equation or this expression that expresses y of k is equal to bt divided by ar plus bs filtering r. Okay, this is the closed loop transfer function in terms of r, s, and t. Now, the second thing I did in this slide is I want this transfer function, which is bt divided by ar plus bs, to be what I have specified. So I equate this. And this is an equation. It's a funny equation because you have polynomials here, but this is an equation, and we are going to learn how to solve it. That is satisfied by r, s, and t. Is it clear now? Now we can actually we can have common terms here, common zeros. Okay, where do these common zeros come? When you have an observer, you create poles, but these poles are annihilated by zeros. So you can usually we call this observer poles, but actually this is a little bit more general than observer poles. because you will need this term if you want to have causal controllers. Okay. So the equation that we are going to solve is not exactly that one, but this one in which we allow some common term here. Okay. And this AO must have all its roots inside unit circle. Now, I want to solve this equation. One possibility is to make R equals to BAM, S equal to 0. So this term is not here. Okay. R is BAM, so, and T is ABM. So what happens is that we have BABM, and here we have ABAM. So everything cancels out and you only have BM divided by AM. So with this choice, you solve your problem. Okay. So one possibility of imposing your closed loop transfer function is this choice. What is this choice? S equal to 0, remember, S is associated to the feedback, so you have no feedback. Okay, this is not good because feedback is an important thing. I'm not able to reject disturbances. And then I just put here the inverse of my system, A divided by B, in series with my desired. So I'm canceling all the poles, I'm canceling all the zeros, okay? And I'm placing here the transfer function that I want. Clearly, this is not a good solution because first, we don't have feedback, and feedback is quite important in control because if a disturbance affects your system, you don't see the disturbance to do some correction of the control action. The other thing is that you are canceling the system. If you are canceling the system, you can get into trouble. Maybe you are thinking at this moment that the trouble comes because you will never be able to have a precise cancellation. But even if you have a precise cancellation, what happens is that suppose that your B is as a root outside unit circle. You are placing a pole outside unit circle, and this pole is unstable. You can say, but it cancels. It cancels from the input-output point of view. That's the meaning of the transfer function. But in the state model, it is there. So you are having a state which is internal. It's probably causing you to go to infinity. And this state is unstable, causes an internal instability. Okay? So this solution that relies on no feedback and pole zero cancellation, that's rubbish. Okay, but it's one solution. Now, suppose that you have another solution. This other solution is selecting these R, S, R, and R polynomials in this way. S equal to T equal to ABM, R equal to this expression. If you replace it, you get again BM divided by AM. Okay? If you do these computations, this choice forces this transfer function to be BM divided by AM. And now what you have feedback. Okay, that is a good thing. But you lost that stuff of the anticipation of the feed-forward term. So probably you can do better because sometimes it's useful to filter the reference. Okay? We say this is just a 1 degree of freedom controller in the sense that we only have a feedback control block inside the feedback loop. Okay, and we are losing the second degree of freedom, which is the feed-forward term. Okay, so this can be made to work. Probably it's not the best choice. You can do better. Okay? So my point is that there are several solutions. Actually, there is an infinite number of solutions, and to this pole placement problem, but they are not, there is a not missing here, not equally good or even acceptable, okay? Furthermore, we could have controllers of higher degrees, but we want to have a systematic way of building controllers with the lowest possible degree, so that your controller is as simplest as possible. Okay, so we must be clever to solve this equation. In particular, there is this story of the fact that you cannot cancel a zero outside unit circle. So if your plant has a zero outside unit circle, you don't want to cancel it. So let's examine this a little bit in detail. Okay, so we want to solve this equation, and we don't want to cancel zeros outside unit circle because this corresponds to placing a pole that is unstable, and from the input-output point of view, the pole does not have a manifestation as long as you are in a linear regime, but probably the input signal will start blowing. There is an internal instability. Okay, so you have to separate your system zeros into parts. The ones that are inside the unit circle that you can cancel if you want, and the ones that are outside the unit circle that you cannot cancel. So I factorize B as a product of these two polynomials. B plus is the good one as the zeros that you can cancel, the well-behaved zeros inside the unit circle. And B minus as the zeros that you cannot cancel, okay? Sometimes you don't want to cancel a zero, so you, instead of placing these zeros that are inside the unit circle, but you don't want to cancel them for some reason. Tomorrow we will see an example. You place them in B minus, the zeros that you don't want to cancel. So B minus contains all the zeros outside unit circle and possibly some zeros that could be canceled, but you don't want them to cancel for reasons related to the performance of your design. Okay. Now, when you decide, when you factorize this polynomial as this product of two polynomials, this does not specify uniquely these polynomials because there is a gain that can be placed here or there. So I assume that B plus is monic. Okay. What is a monic polynomial? A monic polynomial is a polynomial in which the coefficient of the highest degree is 1. For instance, z plus 5 is monic because the coefficient of the highest monomial, which is z, is 1. Okay? Z squared plus 2z plus 5 is again monic because the coefficient of z squared is 1, which is the highest monomial. But 3z squared plus 2z plus 5 is not monic because it's 3z squared. The coefficient of z squared is 3. So this is not monic. So monic simply means that when you write the polynomial from powers from organizing the powers of z or q from the highest to the smallest, the first coefficient is always 1. Okay, so I select B to be monic. Okay, that's a good convention. Now, if you don't want to cancel the zeros in B minus, when you specify your closed loop, you must say that these zeros are there. So your BM, which contains your specification of the zeros, okay, must be a product of B minus, the zeros that you cannot cancel, so they must be there. You are not allowed to say that they are not. plus some b prime m. So that's another thing. That can be, this can be a constant. Okay. But what is essential is that if you don't want to cancel a 0, the corresponding factor must be in the m. When you do the specification, you are not entirely free to do the specification. You must do this choice. Now, b plus, okay, b plus, this is, since b plus is cancelled, okay, there is a knot here that jumped probably from the other slide, okay. B plus is the set, is the term that is cancelled, corresponds to the zeros that are cancelled, okay. So they must be a factor of AR plus BS because these are the closed loop poles. The closed loop poles are going to cancel the zeros that you want to cancel, okay. Now, B plus must be a factor of AR plus BS. So AR plus BS is a product of B plus and some other polynomial, okay? And this is because when you
I think you're muted, Professor.
some strange thing happened here. Can you see my slides?
No.
Okay. Because another window, another Zoom meeting window appeared. I hope this is not an attack. Well, I'm sharing my screen again. Sorry. Now you can see it?
Yes.
Okay, thank you. Okay. So now you can see the slide 293, isn't it?
Yes.
Still can see it?
We can see it.
Okay, there was some problem that I can't understand, but okay. So let's go back. So B plus is cancelled. It must be a factor of AR plus BS because these are the poles. Okay. Now, if B plus is a factor of AR plus BS, it must be a factor of R. Okay. Now, if you want B plus to be a factor of this polynomial, it must be, this polynomial is made of the sum of two terms. Okay. B plus is a factor of B because B is B plus, B minus. Okay. Now here, you know that this is cancelled, so it must be a factor of either A of R, but it must be a factor of R. You remember why? You understand why? Remember that B and A had no common factors, so B plus may not be a factor of A. So when you do the modeling part, you got rid of all the common factors between A and B. So B plus may not be a factor of A, so it must be a factor of R. Okay, so your R must be B plus the zeros that you cannot, that you want to cancel, times some other polynomial that I call R prime. Okay, so let's put everything together. I'm sure you are a little bit lost, but don't be afraid because then we will do some examples and the final algorithm will be clear. So this is the equation that we want to solve. This is the closed loop transfer function in terms of R, S, and T. And these are the specifications, and this is something that we are going to specify. Later, I will tell you how to specify AO. Okay? And now, I split B in the product of two polynomials. B plus is monic and has all the zeros that I want to cancel. And B minus is the remaining part and contains the zeros that I don't want or I cannot cancel. Okay. Now we came to the conclusion that B minus is a factor of Bm and B plus is a factor of R. So we have these two expressions. So let's put all these three things there. So B is B plus B minus, Bm is B minus B prime M. Now, B plus is a factor of R because R is B plus R prime, and this is a factor of B plus B minus. So we put B plus in evidence here, okay? And you write the first equation in this form, okay? So this is just algebra. Now, we can simplify things because B plus, you can do this cancellation, okay? Usually we say cut, but you should be careful because when you cut a zero with a pole, you are considering a different system that has a different transient response. You are canceling poles, and poles correspond to something that affects the transient response. But since the roots of B are inside unit circle, these terms here correspond to a transient that goes to zero. So we just say we cancel them. Okay. Now we have here, we cannot use the same argument because B minus has roots outside unit circle. So I cannot say, well, I divide by B minus and then I cut B minus with B minus. Okay. The argument here is a little bit different. You write this as several equations corresponding to the different coefficients of B minus, and everything on the left is that multiplies the coefficient is equal to everything on the right that multiplies the same coefficient. So this transfer function must be equal to that one, and actually I can cancel the B minus. Okay, so I end up with this simpler set of equations. Okay. Now, you see immediately that T must be B prime M AO. Okay. Remember that B prime M comes from the beginning. Let's see. When you do the specifications, you specify BM, but you should be careful because BM has two parts. One part is the zeros that you cannot cancel, and B prime M is the remaining part. Sometimes this is just a constant, okay, but it's something. Okay, so you specify B prime M, and T is nothing more than B prime M that you specified plus AO that you also specify. I will tell you how to specify AO later. Okay. Now, the denominators must also be equal. So A R prime plus B minus S equals to AM AO. But you can say, well, R prime is Z minus 1 lambda, R prime 1. So actually, because you are forcing the integrators, sometimes remember that lambda is a number of integrators, can be 0. In this case, this is just 1. It's not there. Or lambda is equal to 1. So you have already polynomial T, and polynomials are R1 prime, and thus satisfy this equation. Okay? In polynomials, if you have R prime 1, then you multiply by Z minus 1 up to lambda, you get R prime, and then you multiply again by B plus and you get R. Okay? So this equation defines R and S. This is a new type of differential algebraic equation called a Diophantine equation. The unknowns are R1 prime and S. Have you met this type of Diophantine equations before in some other course? Perhaps in computer science, related to computer science or digital systems or something like that? No? Coding? Okay, but it appears. So let's see some basic things about these equations. Okay, so let's do a small detour about the Diophantine equation. So a Diophantine equation in polynomials is something like this. A, B, and C are polynomials, non-polynomials. Okay, forget about the transfer function. This is just a general polynomial A, general polynomial B, and general polynomial C. And X and Y are the unknowns. They are polynomials that you want to find. Okay, and two questions that you want to answer is: are there any solution? If there are solutions, is the solution unique, or an equation might have different equations, different solutions? Okay, the polynomials that form the solution of this equation, the so-called Diophantine equation, exist in an algebraic structure called ring. Have you studied basic notions of algebra, like groups, for instance? You know what is a group in algebra? Have you ever studied that? Já estudaram, alguma vez estudaram o conceito de grupo na álgebra?
Penso que não.
Okay, so it's not important. Okay, a group is you have a set and you have an operation in the set. For instance, imagine numbers and multiplication. Now you can have different types of numbers. Okay, suppose consider algebraic rational numbers given by the fraction of two integers, números racionais, quocientes de números inteiros. Okay, together with the multiplication operation that you know. Okay, you have a number of properties. For instance, there is one number such that given any other number, for each number, you can find another number that pairs it, and such that the multiplication of both of them gives the other number, which is called the unity. So the unity in multiplication is 1, the neutral element, better to say. Okay? In the rational numbers, you can also have, so the inverse operation of multiplication always have a solution. Okay? So with properties like this, you build a group. For instance, the set of integer numbers with multiplication is not a group because you don't have an inverse, notion of inverse. Now, a ring is you have two sets of operations, so the same set of numbers, but with two operations, say multiplication and addition. Okay, and you must have, in addition, so the set with each of these operations must be a group, and in addition, you must satisfy the kind of distributive operation. That's a ring. Okay, so integer numbers or rational numbers with even integer numbers, they form a ring, and polynomials also form a ring. Okay, but this is just a definition. If it rings a bell to you, it's okay. If it does not ring a bell, okay, forget it. Now, we have, what is important is what are conditions such that we have a solution, and what are the conditions for the solution to be unique, or is the solution unique? Okay, and the idea of the story of the algebraic structures is that you can study different sets, and the properties are the same. Okay, so instead of giving an example with polynomials, I give you an example with integer numbers. For instance, suppose that you have this equation, 3x plus 2y equal to 5, and my set now is the set of integers. Okay, and if you select x equal to 1 and y equal to 1, this is true. So you have one solution. Now, if you have one solution, it's very easy to build many other solutions. You just multiply one of the solutions by 2n, so you replace x by the solution that you found, the particular solution that you found, plus the coefficient of y times some number n, and y is the particular solution for y minus the coefficient of x times n, the same n. When you vary n, you get solutions. Why? Because these two terms will cancel out. Okay? It's very easy to prove that if x0 and y0, for instance, if x0 is 1 and y0 is 1, then if you satisfy this equation, then any pair of numbers x and y that satisfy these expressions for any n, any integer n will satisfy this equation. So this means that if in this type of equations, if you have one solution, you have an infinite number of solutions. Okay? The solutions form a affine space. Have you heard of affine spaces? Probably not. But affine spaces, for instance, are important in image processing. Okay. So remember this. Remember this. If we have one solution, then there is an infinite number of solutions that you can build in this way for integers. For polynomials, it's quite the same. Now, sometimes you don't have a solution. For instance, 4x plus 6y is always even, a simple número par, because we have a number 2 that is common here. So no matter the values of x and y that you place here, this number will always be even. Okay? But you should select x and y to be 1, which is odd, an odd number. So, à esquerda é sempre par e à direita é um número ímpar. So this has no solution. Okay? And what happens here? If you compute the maximum common divisor of 4 and 6, that is to say, the biggest integer number that divides both 4 and 6, it's 2. Okay? And this maximum common divisor does not exactly divide 1, because 1 divided by 2 is 1/2, which is not an integer number. Okay? So we said that the maximum common divisor of 4 and 6 do not exactly divides the right term. Okay? So this fact in general, for a solution to exist, the maximum common divisor of the coefficients on the left must divide the coefficient on the right. Okay? And in polynomials, you have quite similar results. What is the division of polynomials? How do you define the division of polynomials? I say that Q is the quotient of B divided by A, or that A divides polynomial B if B is equal to AQ. In general, this is not true. And the only thing that you can find is that B is equal to AQ plus R, where the degree is not the absolute value of the coefficients of R, but it's the degree of R is smaller than the degree of A. Okay? Remember that this symbol reads the degree of the polynomial. Okay? So sometimes we say that A exactly divides, or simply that A divides B. Let me give you an example. Suppose that A is this polynomial, B1 is this polynomial, and B2 is this polynomial. Polynomial A is divisible by B1, okay? Because B1 is Z plus 1, so what you get as the quotient is 5Z plus 2, okay? But, and A is equal to B1Q, okay, where Q is the quotient 5Z plus 2. But A is not divisible by B2 because you have a remainder. You cannot find a polynomial such that Q times B2 is exactly equal to A. No, you have to add this here. Okay. Now, another notion is the notion of maximum common divisor. I represent the maximum common divisor of polynomials A and B in this way. So it's between the curved brackets A and B. And the maximum common divisor is a polynomial that divides simultaneously A and B, and that's the maximum degree. Okay? Now, this is the most important result. Go back to the Diophantine equation in polynomials. Okay, so the Diophantine equation AX plus BY equal to C as a solution if and only if, read this as if and only if, this is not a misprint, it's if and only if, the maximum common divisor of AB divides C. Okay, so the maximum common divisor of the coefficients on the left that are polynomials, they exactly divide C. Okay, in particular, if A and B have no common roots, the maximum common divisor is just the number 1, which divides exactly C, and this equation has at least one solution. If you have one solution, then you have an infinite number of solutions that can be generated in this way. So x0, y0 is one particular solution, and t is something, is any polynomial. Okay? Now, since we have many solutions, actually an infinite number of solutions, suppose that we are in the case where the maximum common divisor of A and B divides C, we can impose a condition such that with this condition, we just get one solution. And the condition is that either the degree of x is smaller than the degree of the coefficient of y, or the degree of y is smaller than the degree of the coefficient of x. So either one or the other. It corresponds to different conditions. Okay. Now, let's apply this to our pole placement problem. So our Diophantine equation is this one. The unknowns are r prime 1, okay, this is an unknown, and s, and we have as coefficients this a, z minus 1 up to lambda, b minus, and then on the right am, ao. Okay. Now, if b minus has no common roots with a, then the maximum common divisor and no roots at 1 also. Okay. Then the maximum common divisor of these two coefficients is 1, and 1 exactly divides am, ao. Okay, so you see the importance that we did at the beginning, that A and B had no common roots. A and B no common roots means that A and B minus no common roots, because B minus is a subset, as a subset of the roots of B. Okay, so this equation has a solution. Actually, it has an infinite number of solutions corresponding to different controllers. So there is an infinite number of controllers that you can use. But you want to use a controller with minimum complexity, so you impose the fact that the degree of S is smaller than the degree of A multiplying Z minus 1 up to lambda, or lambda plus degree of A. Okay, and in this way, you know that you have one solution and only one solution. Okay, applying the result of the previous slide. And in this way, by making some computations that I'm going to skip, if you want, I can give you all the details, a text with all the details. Then the degree of R1 prime is given by this expression. Okay. Now, we have also causality. And you can prove this inequality. Okay. So the degree of AM minus the degree of BM, so the difference between the number of poles and zeros that you specify must be bigger or equal than the degree of zeros in pole minus poles of the open loop. Okay. So in closed loop, you cannot decrease the excess pole zeros. That's what I mean. And this will impose some constraint on the number of zeros. Furthermore, and this comes from causality of the controller. Furthermore, for the controller to be causal, you have to select a O with a minimum degree given by this expression. Okay, so let's put everything. I'm not going to show it. It's a little bit cumbersome. If you want, if some of you want, I can give you a text with this, with the proof of these expressions, with the deduction of these expressions, which is not difficult, but it's a little bit tedious. So let's sum up what we have, the algorithm, the design algorithm, and tomorrow we are going to see some examples. Now, what is the data? You must have a process model, B and A. So how do you get B and A? You get it from identification, the first part of this course. Okay, and the specifications, you must specify the position of the zeros and the poles, BM and AM. So the zeros are the roots of BM, the desired zeros are the roots of BM, the desired poles are the roots of AM. When you do these specifications, you must satisfy this condition. The excess pole zeros of the desired system must be bigger or equal than the excess pole system of the process model. The difference between the poles and zeros, the number of poles and the number of, is the delay of the system. So what it says is that you may not reduce your delay. You can only increase it or keep it the same. Usually you keep it the same. So because you don't want to increase the delay in response. Okay. So you can, if you would do a design in which you reduce the pure delay of the control system, your controller would not be causal. Now, you must select this BM and AM, and you must specify the number of integrators, lambda. Usually it's 0 or 1. Now you factorize B as B plus B minus, where B plus has all the zeros inside unit circle, and B minus has all the zeros outside unit circle, or zeros that are inside unit circle but that you don't want to cancel. And B plus must be monic. That is to say, the coefficient of the leading term must be 1. Now, your BM must satisfy, must have as factor B minus. Okay, so the zeros that you don't cancel must be specified in the zeros that you want in the closed loop, because if you don't cancel them, they are still there. Okay, and you must find AO that satisfies this causality condition. Okay, take for instance, later we are going to discuss this with more care, but take for instance Z up to the minimum degree. Okay, so compute this number on the right and select AO to be Z up to this number. Okay, later we are going to study this. You know everything here, so this is the degree of open loop denominator polynomial, desired denominator polynomial, number of zeros to cancel, number of integrators. So you know everything here. Now compute T equal to B prime M times AO. B prime M, remember, came from this factorization. Solve this Diophantine equation with respect to R prime and B minus. And you impose this. The degree of S must be smaller than lambda plus degree of A. And the degree of R prime must be given by this expression. Now, in practice, what do? You plug here general polynomials that satisfy these conditions and use the method of unknown coefficients. Okay? Once you get, you get already S and T. To get R from R prime, you just multiply by B plus and Q minus 1 lambda. You get R. Okay? Now, at this point, you are probably in panic. Okay? Let me tell you two things. First, you don't have to know these expressions by memory. I write them in the test when there will probably be one problem in the exam, in the second test about this. But I write these expressions in the test. And the other thing is that this looks very complicated, but once we start doing examples, it's very simple. It's very simple. So before we stop, is there any question? Okay, if not, probably tomorrow there will be more questions because we will do some examples about this algorithm. So we meet each other tomorrow at the same time. Bye-bye.
Professor,
Sim.
uma pergunta. O professor pode só esclarecer-me uma dúvida que ainda relacionado com a matéria que vem para o primeiro teste, que eu ontem tive a rever umas coisas.